So now we move to, I think Gaussian is the next topic. Normal random variables, yes. Normal. So here we would like to show that the main result is that if you have a sum of independently distributed random numbers, independently distributed normal random variables. So suppose that xi are independently distributed normal random variables. And I use the following notation. I use the notation that I say that x is a normal mu sigma square if it's a normal distribution with mean mu and variance sigma square. So the PDF of x is fx of x is equal to 1 over the square root of 2 pi. There is a sigma, and then there is an e to the minus x minus mu squared divided by 2 sigma squared. Right? So the claim is the following, that suppose you have xi, so xi are independent in their normal mu I sigma I squared. Then I take that the function z is the sum I equals 1 to n of xi. The claim is that z is a normal distribution mu sigma square with mu is the sum of mu I and sigma square is the sum of sigma I square. So the claim is very simple. If you sum n independent distribution normal random variable, the sum is also a normal random variable. The mean is the sum of the mean. The variance is the sum of the variance. The claim is extremely simple, right? And so that's what we plan to do. I don't like the way the book does it, so I'll do it a slightly different way. I hope you don't complain. I hope I do it in a simpler way, but that's necessarily true. So the first thing we observe is the following. First observation is that if x is a normal mu sigma squared, I can write x is mu plus some x tilde, where x tilde is a normal 0 sigma x squared, right? So the first claim is that if I have a random variable which is normally distributed with the mean mu, I can always think that this random variable is the sum of the mean plus another random variable, x tilde, which is 0 sigma squared. And the proof is, I think I can leave it as exercise, because the PDF, the PDF, I think that we have done things like this, right? So the PDF of x is there. So what is the PDF? Probability that x tilde. How do we do that? The probability that x is less than a, no, x tilde. Probability that x tilde is less than a is equal to the probability that x minus mu is less than a, because x theta is x minus mu. And so this is equal to f x of x minus mu is this useful? Not necessarily. Is it useful? I'm not sure it is useful. Right? That's we have done this. This is the, in all our exercise. This is the quantity we call the z, which is the mean, the function in which we remove the mean and divide it by the standard deviation. So this is the transformation that we have been using, right? So that's phi of a divided by sigma x. So this is a zero mean, and so it is clear that also x tilde has a zero mean. So that's the first observation. So what does it mean? It means that consider now n is equal to. N is equal to, so z is equal to x1 plus x2. And I can write as mu1 plus mu2 plus x1 tilde plus x2 tilde. Right? So, and this means that now I care about, so if I take the expectation value of z, of course the expectation value of z is mu1 plus mu2, because the expectation value of these two is 0. Good. So, this new random variable, the average is the sum of the average. This is easy. The hard part is to show that the distribution function, the density function is the one of a normal distribution, and that the variance is the sum of the variance. That's the hard part. So now we want to plot, so we have now this quantity z tilde, which is z minus mu, why did I call it mu1? Okay, because 1 and 2, mu1 is mu. I want to show that, what is this? This is x1 plus x2. So I want to show that if I take two normally distributed random variables with zero mean, the sum is another normally distributed random variable with zero mean, and the variance is the sum of the variance. Okay? So, for convenience, instead of writing, I eliminated the tilde, and I eliminated 1 and 2, and I call this x and y. So now the claim is the following. Now I has n equal to, so this means I take z is equal to x plus y, and x is a normal 0 sigma x squared and y is a normal 0 y sigma y squared. It is easy. It is easier to do the calculation if these are 1 and 1. If these are 1 and 1, then you show that the result is a normal distributed random variable with the sigma squared is equal to 2. It's the sum 1 plus 1. But I think we can do the general case. We can do this. It's not too complicated. Okay, so how do we do that? Convolution. So this means we know that, so what is fz? This is, you have to do the convolution between these two. So this one is 1 over square root of 2 pi, sigma x. And then you have to do the integral. Well, when you do the integral, there is a factor 1 over square root of 2 pi sigma x, and then there is another factor 1 over square root of 2 pi sigma y. We can factor this out of the integral. And then we have this integral. The integral is the integral from, finally the integral from minus infinity to plus infinity. I don't have to worry about the boundary. Minus infinity to plus infinity. And then you have e to the minus, and here, what do you have here? Here you have x squared divided by 2 sigma x squared times, here you have, and here you have z minus x squared divided by 2 sigma y squared. And you integrate this in the x. That's the convolution you want to compute. Okay? This part is fx. This part is fy computed in y equal z minus x. Okay? That's what we want to compute. And we observe that, so this is equal to 1 over 2 pi sigma x sigma y times the integral minus infinity plus infinity of exponential. There is a minus, there is 1/2, and then there is some polynomial, this polynomial p of x and z. And what is this polynomial p? I think we can use the other blackboard to see what this polynomial is. Let's see, what is this polynomial? This polynomial p of x and z is equal x squared divided by sigma x squared plus z minus x squared divided by sigma y squared. Okay? So this is equal to there is the x squared, there is a 1 over sigma x squared plus 1 over sigma y squared, comes from here. Then there is a minus 2. What is here? There is an x. There is a z. And there is a sigma y squared. Right? The denominator. 2x. There is a y squared in the denominator. Right? Plus z squared divided by sigma y squared. Okay? This quantity here we can write 1 over sigma x squared plus 1 over sigma y squared is equal to sigma x squared, sigma y squared, and then in the denominator you have sigma y squared plus sigma x squared. Do you agree? Good. For simplicity of notation, you will be allowed to call this object here sigma squared. I define a new quantity called sigma squared, which is the sum of the square. So I write this as a sigma squared divided by sigma x squared, sigma y squared. Fine. So now we can rewrite this as in this form. It's x sigma divided by sigma x sigma y squared, right? Because that's sigma squared divided, right? The first piece. Minus 2x divided by sigma y, and there's a z sigma y. And then you have a plus z squared divided by sigma y squared. Now, what is the idea? The idea is the following. You would like to find, to write here, a perfect square in x. You would like to do something like some object like alpha x plus beta z squared. Why? Why do you want to do that? The reason is that, where is that this polynomial appears? This polynomial actually appears here. So at a certain point, you will have an integral of an exponent into the minus 1/2 of an object like this. And then you integrate, x goes from minus infinity to plus infinity. With a change of variable, this object, this quantity doesn't, there is a translation invariance. The integration goes from minus infinity to plus infinity. So with a change of variable, this quantity has no influence. So this will give you a number. That's what you want to do. So the objective is to write a square. This reminds me of very old things that you learn in school when you want to find the roots of a quadratic equation. You try to to write things in the form of a square plus something else. Right? It's very simple. So what you do here, you want to write as a square. Okay, so that's already a square. This is the cross product. So if this is a cross product, you have 2 times there is an x. So you want to put a sigma here. And you put a sigma here. And then you want to put a sigma x here. So you have to put a sigma x. Fair? Okay, so this is now the cross product. But wait a moment. We miss the square of this object here. Well, you can add. We need the square of this. Let's add it. But if you add, you have also to subtract. Right? We add and subtract. Now this one is a square. So this quantity here is polynomial. Is p of x and z is equal. It's a square. It's sigma x divided by sigma x sigma y minus z sigma x divided by sigma sigma y squared. plus this. There is a z squared over sigma y squared. You can factor this out. This is 1 minus, so this times this minus sigma x squared divided by sigma squared. Actually, this can be simplified a little bit because 1 minus sigma x squared divided by sigma squared. Sigma squared was sigma x squared plus sigma y squared. If you subtract the sigma x squared, this becomes sigma y squared. So this whole piece becomes sigma y squared divided by sigma squared. Can I do that? And this can be simplified further. Okay, now we are ready to do the substitution. Now, this is the integral, but wait a moment, there is a piece in this polynomial which is e to the 1/2 of this, the piece of this polynomial does not, there is a piece that does not depend on x. This piece here does not depend on x. This can be factored out. So we can safely factor out e to the minus 1/2 the piece that does not depend on x. It's this one. Z squared divided by sigma squared. And then you have the integral here. The integral is e to the minus 1/2 of this whole mess here. This whole mess is sigma x divided by sigma x, sigma y, minus z, sigma x divided by sigma y. Dx.
Square. This is square.
What?
Yeah, the square.
Yeah, I didn't finish right.
Okay.
So yes, so that's the quantity. Now we can either use the trick we said before. This quantity must be somehow normalized automatically, and so you already see that this is a Gaussian distribution with the parameter sigma squared mean equal to 0. But if you want to be a little bit pickier, then what you can do is that you observe that, as I said before, this parameter does not matter. I leave to you as an exercise to check that everything can be written in terms of some x minus something. This is an x minus, you can factor out sigma x, sigma y, you can factor this out, and then this will be x minus something. And this something does not matter, because you can make a change, a translation, you can make a change of coordinates, and this does not matter. What matters is this piece here. So you need to make a change of variables. When you make a change of variables, you multiply this by, the change of variable is x times sigma divided by sigma x, sigma y is equal psi. And then the x is equal sigma divided by sigma x, sigma y, dx. So this integral here becomes the integral from minus infinity to plus infinity of v to the 1 minus 1/2. This doesn't matter. You have a psi square, and then this dx becomes sigma divided by sigma x, sigma y. Big psi. The x, no, it's the other way around. The x is equal sigma x, sigma y, big psi, divided by sigma. So this is big psi, and then you have sigma x, sigma y, divided by sigma. Would you agree about that? So I can replace this integral, I put it in place of this one. So this is sigma x, sigma y divided by sigma. Sigma x, sigma y divided by sigma. And this integral is the integral of minus infinity plus infinity of e to the minus x squared over 2 big psi. Oh, well, wait a moment. I can write it this way. Square root of 2 pi here, square root of 2 pi. But we know that this, we've done it, this quantity is equal to 1. So when we simplify this expression, that's the end. The end is that it's 1 over square root of 2 pi sigma e to the minus e square of sigma square, which is exactly the PDF for Gauss, right? We've done it for n is equal to 2, but then of course, by induction on n, you can prove that this is true for all n. So this is true for all n. By induction. Okay. So give me 2 minutes of break. I have to start the movie again, and then we go on.